Yes, hello everybody. We are a company Rankos, which is a joint venture Russian-Italian company. And I would like to present our team. We have met 1 year ago here at Santander at the geopolymer camp. And this acquaintance led us to organize in our company for application of geopolymers for various purposes, including 3D printing. So the topic is 3D printing, but this presentation is not only about this application. It's about the application of geopolymers that we have done and what we are planning to do further as well. So Alex Sergiani is our main technician, our brain center, who is creating the recipes of geopolymers itself. Andrei Dudnikov is in charge for organizing the work of our laboratory and of our production site. So he's in charge for everything.
So, and Marina is in charge for tick analysis to make everything faster and economically, because
yeah, if they create too expensive composition, nobody will need it. So a little bit about our region. Chelyabinsk region is in the south of Europe. You can see it in orange. Ural Mountains are the oldest mountains in the world, which means that they are quite eroded, very low, but they have revealed all their treasures, and we have a lot of deposits of minerals. Whatever you can imagine, minerals exist in our region, including iron, copper ore, zinc, precious, semi-precious stones, calcite, marble, kaolin, and metakaolin is also produced in our region. Yeah, and so the main materials that can be interesting for geopolymer production are granulated blast furnace slag, metakaolin, fly ash type F, microsilica, and soluble silicates. And now a little bit more about each component, about each resource. My colleague.
Yes, and we have all these sorts of materials within 200 kilometers from our site. So the blast furnace granulated slag, it's two major producers of iron in Russia located in our region, and one of them is Metshel, for whom we made a research in 2013. They installed a vertical mill, dosha, and video, and we have carried out a research project for them to adjust different types of grinding of this material to be suitable both for OPC application and for geopolymer application. This is the process, how it works, and it's a closed system with a separator inside, and dry up to 24% of moisture blast furnace slag comes into the mill and it's grinded on the table, and the particles go through the separator up to 6 times before they get in very dry, about 0.1% of moisture, and the fineness of these particles are represented here. It's an average D50 is 11 microns, and mineralogical composition is presented by 98% of amorphase, and some crystalline phase is represented mainly by melanite, and there is a chemical composition also here. You can see that it's rich in calcium and other minerals also, and the specific area is 4,500 and 5,000 cubic centimeters per gram, which is not good for geopolymers because it's, as Professor Davidovich clarified us, it provides fast setting, and if we had the possibility to grind it less fine, it will be better. Yeah. So next material is metakaolin. We have a supplier of the only supplier in Russia of metakaolin, producer of metakaolin, it's Zhuravlin Law Company. They're located also in our region, and they have quite good metakaolin suitable for geopolymer applications. We made one of our recipes based on this metakaolin, and as they said, it is made at around 750 degrees Celsius in rotary kiln. and it has very high amount of morphase, about 92%, and the particle distribution is not so good, but it's very good for geopolymer applications, bigger than the other suppliers on the market. So we have two power plants who supply us with fly ash. One of them is Italian company Enel, which it's located in 200 kilometers, and the other one is located in our region, but they started this year to produce about 4 days ago type C fly ash, which is, we're not familiar with it, and we're thinking about how to apply it, but anyway, we have another source of fly ash. And we have a microsilica as well. It's in the city located an electrometallurgical plant which is produce microsilica. It's black in color and it is dense. That is why the granulometry is not so fine. Also, it's 19.78 microns, D15 average. But it's quite good for geopolymers, and we use it. And this is a light gray color. It's a byproduct from pure silica production plant, and it has high amount of silicon and 99% morphase. And we also, Chelyabinsk region is the oldest, biggest, has an oldest and biggest open coal quarry in Eurasia, and as a result of coal mining, large amounts of burnt rock accumulated near the shafts. And its chemical mineralogical analysis are very close to metakaolin, and we are looking for application of this material. It has 28 to 35% of amorphase, as Professor Davidovits also said that it is enough for construction application. It is enough to get 35, to get 30, to get 25 MPa. You don't need high reactive materials like metakaolin, pure metakaolin, or you can reduce its amount. Well, we are looking forward to using this material, but it is not grinded. It's a coal quarry. It's one of the biggest in USA located, and in South America. Sorry.
And this is the second one.
And the second one. And this is the coal mining waste, which are located wherever you see. So, and one of two major producers of soluble silicates are located in Chelyabinsk region, and they supply raw materials to producers of water glass all over Russia. And based on their materials, we started to produce a silicate suitable for geopolymer application. We make an adjustment. We take a stable material, which is made in a furnace process, and then we have potassium-based silicate in general, and we can make it a sodium, but sodium has its disadvantages, as all of you know. And one of the new materials come to our region recently in 2013, the third strike. We haven't discovered it yet, and it is possible to apply in geopolymers, but there are some new materials not known. Okay.
A little bit of background of from Soviet Union. As you know, Bukhovsky had his school in Kiev of alkali activated materials, and his school was very popular in our region because of huge deposits of metal waste, like granulated blast furnace slag, and a lot of scientists were occupied with alkali activation materials, but they have their drawbacks. As we know, it's not stable. They have not stable properties, and also it's granulated slag is very hard to mill. So if you don't have good mills, and it consumes a lot of energy to mill granulated slag, and nobody was very much counting in Soviet era. They didn't count money very well, so they did grind this slag and they applied it everywhere. But as soon as Soviet Union collapsed, all these disadvantages made the technology gradually forgotten. And so, but still, this is our legacy, our heritage. And so, Next issue is the standardization issue, which is common for alkali-activated materials and for geopolymers. There are no standards right now which can allow using of both materials in construction. In Russia, yes. In Soviet Union, there were more than 65 standards that allowed application of alkali-activated materials and geopolymers, because geopolymers are also have alkali in their composition. But as soon as the Soviet Union collapsed, the whole passages were just taken out of the standards and they exist no more. We have found them in Ukrainian standards, they are still there, but not in Russian standards, unfortunately. And now we are working in collaboration with the National Association of Developers, which are situated in Yekaterinburg, not far from us. And we hope in the future, in a few years probably, to create a new standard which will allow the implementation of geopolymers in construction and road construction. Okay. And so, a little bit of Italian heritage.
Very little, because I think in the book of David that you can find all information about, and I tried this information for this in this book. This is very interesting. And from Italy, first signs of geopolymer crisis are from Etruscan, and then the best moment for this kind of application of type of product was with the beautiful old Romans construction, and with the bit using the technology about named opus siginum or carbunculus, that are two types of Roman cement, and uses lime and pozzolana, natural pozzolana from the Vesuvius volcan and Campi Flegrace. And so after 2,000 years and more, I think it would be the right time to reuse this technology.
So coming back to the main topic is 3D printing. Recently, this winter, we have been contacted by the company Apiskor, which is based in Irkutsk in Russia, in Siberia. It's a group of young engineers who invented a mobile 3D printer which can print buildings up to 100 square meters, and they claim that it can build a building of this size in 24 hours. So they met some difficulties with ordinary Portland cement-based concrete, and all you know that they need adjusted setting time, they need a thixotropic concrete which will hold its shape for several layers, and so they came to us, and here is a small presentation of their technology, of their printer.
Introducing a new mobile 3D printer from Apiskor Engineering. Modern 3D printers are notable for their massive bulk, which significantly complicates the process of transporting them and assembling them at the construction site. It also multiplies the building's prime cost many times over. To solve this problem, we've developed a compact 3D printer for construction projects with a low to medium number of stories. Our device's primary distinction is its low weight and size, which eliminates the need for special transportation and significantly simplifies the process of delivering the printer to the construction site. The device's construction is designed to make it easy to assemble on any surface without repairing the area in advance or performing tests during the assembly process. The printer's swiveling extruder head allows you to print a building on 2 planes at once. Moreover, the printer's construction area is up to 1,500 square feet with virtually unlimited height. Thanks to its proper power consumption, high operating speed, access to waste material, and savings on labor, our 3D printer will allow you to significantly reduce your construction costs. Learn more about our mobile 3D construction printer at apiskor.com.
And so, we have prepared several recipes of geopolymers. We went to their site in Irkutsk. We carried out the first small tests, and you see the result here on the table. It's the result of our small tests. These are 2 different compositions of geopolymers. The guys just glued it together to be easier to transport. And after that, in February, they started constructing a full-scale house on their site in Irkutsk. You see, it should be protected from the atmosphere because it's minus 40 in Irkutsk in winter, so no printer can work in such conditions. So this is the process of how they construct the house.
Yeah, and as you can see, it's a bitumen on the surface. It's obliterated according to our regulations. We all know that geopolymers are water resistant. You don't need it to put it on, so it's just our system. And these guys were designed to show the possibilities of geopolymer cement, geopolymer concretes, and but the price of them were very high for industrial application, and we redesigned a recipe using a fly ash and slag based, and this is one. It's cheaper and it's comparable to the price of ordinary Portland cement with the desired properties they need. They have built half a house, and then was a huge hurricane, and the coverage was destroyed, and now they are build it again. We continue to build, but we don't have any videos yet. And they have a plan to build. They have a house, a Dima house in Austria in this September, maybe a little bit later. There is a village of Harbis, and they present different technologies of printing, of building construction. So these are the Episcore needs. What they needed adjustable setting time, because if you have a big house, you need a prolonged setting time. If you have a small house, you need a short setting time. So they're looking for this parameter. So they also wanted good flexural and compressive strengths to be structural, and they wanted a fireproof and more waterproof material, because they build basements of the houses and they don't need to cover it with any other materials. And they also wanted good compressive strength in a short period of time to allow print as fast as possible, to allow to put one layer after another. And we designed three types, Alex designed three types of mixes: in black, super performance I call it, and beige MKSM 350 based, and gray fly ash based geopolymer. So he will describe the results. Not yet. It's a video of printing black super performance concrete. We adjusted, on this video we have adjusted the settings of the printer to print the geopolymer, and it might be like this. When it goes too fast, you can see it slips, and there was lots of problems, but we solved it finally. And it goes. So we used here a fly ash and slag with addition of microsilica and geosilicate, a soluble silicate solution, potassium based. Okay, and it was beige, and this is a gray one.
And this is about performance. So the black super performance is the most performant. Has a certain time from 45 minutes to 60 at 18 degrees, and a viscosity isotropic by shock table test. A density of 2.2 grams on cubic centimeters. Ability to harden at minus 20, and after defrost in 2 hours at 20 degrees. I tested and I found 2.3 megapascal of flexural strength and 6.2 about compressive at only 24 hours, so big good result. freeze thaw resistance 500 cycles, Russian norm, and water resistant W18, other Russian norm. And this is the development of mechanical strength in compressive, and in flexural. And all these kind of recipes are without fibers, but I have intention to improve using basalt fiber to pass also the test about the earthquake areas. So in modifying a little the binder to add more flexibility to the binder, and I think I'm optimistic. And this is the second one, based on metakaolin, and the setting time is a little more long, is from 19 to quite 2 hours, even at 18 degrees. Viscosity remains isotropic, density 2, ability to harden at -20 verified, and 1 megapascal of flexural strength, and 5.2 of compressive after only 24 hours. Freeze thaw resistant 500 cycles, and water resistant W16. And the mechanical strength final are 72 on compressive and quite 10 on flexural. The last, the more cheaper and gray one, based on fly ash, setting time from 60 to 2 hours, from 60 minutes to 2 hours. At 18 degrees, the thixotropic density little more, 2.3, ability to harden at -20 verified, with a little lower strength, of course. Flexural 0.5 megapascal after 24 hours, and the compressive about 3.1. Freeze thaw resistant 400 cycles, and water resistant W12. And the final mechanical strength 34 megapascal on compressive, and quite and almost 9 from flexural.
So as you can see, we don't need 100 megapascal constructions. We need only 44, but we lower the price and 10 times.
Oh.
Okay. So we made a mixing process a very strange way, because we were in the field, they were not prepared, and we had to adjust our technology to make it good. And yeah, and the filler, the sand was not so perfect on the site as we suggested them to use. So the result you see, it was replied in laboratory after, and these samples a little bit less in performance.
Yeah.
But anyway, it has passed all the tests. So we are preparing binder in this thing. It's quite long process, and then we finally somewhere add a filler.
Broken one drill.
Yeah.
Broken
And then you push this material, this ready geopolymer, into pumping system. They use Putzmeister pumping system, just like this one. This is why we started thinking about a mixing system for geopolymers, for 3D printing, and for general application, and Alex will tell you about it.
Yeah. The problem about the geopolymer until now was the movement. So if you have the possibility to have a center beton near to the job site, perfect. But if you need to make kilometers in summer, or like in Russia, that they consider near 500 kilometers for them is near, and so for materials already mixed could be a problem. And so with my father, that is a designer of plant designer, we created this solution, and we verified in a pilot plant that is already available, and now we have to product in series, And this is the production is ensured by two mobile 94 liters of capability mixers, self-rechargeable system, reproduce geopolymer concrete in continuous cycles. So these are the mixers are there, and there are two that work simultaneously, and the powders, reactive powders inside, the aggregates inside, and the water to clean, and the liquid. And then the production is all the plant are located in a truck of 22 tons. So we produce only when we arrived on the job site, and we produce only the material that we have to produce, not more. So we have a lot of efficiency in mixing, in durability, and in fast cleaning, and it's very easy to use because the system is empty panel with the comprehensive indication, and it's possible to control all setting in next future, but because my electronic have already done this thing through an application on a tablet or smartphone. So it's not necessary that the operator knows what is a geopolymer, what is the complexity of the mechanism, because he doesn't touch physically the material at this stage. And this is how the plant in the practical, and it's possible to have a recharge of materials in a in a trailer. I don't forgot the word. And that's all.
Thank you.
That's all for the next
For the plant.
Just 2 minutes more.
Yeah.
So we want to share with you our future plans and projects. So we have a company with architectural concrete application and countertops, panels for wall covering, and we continue to use the geopolymers in this sphere. And we also have a project with a Moscow company who makes a natural filling with the soil stabilization, but in this geopolymers, the water binder ratio is 1.0, 4.0. It's quite high, and there is a problem with efflorescence, a huge problem with this, because the structure cannot be firmly made with this amount of water. We have a project with water storage system for civil use, and these are projects which are already running. It's an insulation panels and finishings. It's Alex team work on it with the company Harris in Italy, and the other one is high voltage insulators. We have a company of Global Insulator Group. In these insulators, inside to connect a glass with each other, they use these steel fins, and these steel fins connected with the glass using cement-based, geopolymer cement-based mortar. So we are making an alternative to this cement-based with a geopolymer. So, and also we have a plant who produce arborline blocks. It's wooden blocks, and also panels which are not allowed to use in Russia, but in Italy since 3 years they are happy to use it and live in these buildings. So our project and technologies, we are supplying raw materials, we are supplying geopolymer cements, we are supplying 3D geopolymer cements and mobile mixing plant. These are our products. Thank you.
ounces. Now we are in the centimeter, millimeter range. Too small. Okay? So, first question. To whom?
The question is to all the panelists, because they've all indicated the same process change. That is, you have an additive. Have you used superplasticizers or boron? What are you using as an additive?
I don't use any super plasticizer at all.
Okay.
Because of price, because of temperature, because of mechanical strength that we have promised. So I have to respect certain reaction. I'm not sure with a super plasticizer I could reach similar mechanical strength, because in laboratory the black one, that is the smaller sample this, I found 105 megapascal. Then in reality, in job site, we obtain only 96. But there is a difference of mixing, of temperature, of all the conditions that Ralph specified very well. And so we don't use any additives.
Okay, and since there's no microfibers added,
Yeah.
is it considered too brittle for some applications?
I think in this kind of recipe has a ratio between silicon and aluminum enough to guarantee stability. But if we have to use in earthquake area, I can put inside basal fiber, long basal fiber that permit I have made a trial in a laboratory. I obtained at room temperature after 7 days. I obtained, because is last day, and I obtained 15 megapascal of flexural. In comparison with I remember 7, 8.
Yeah,
so quite double.
Okay.
And so is good.
So were the other groups use superplasticizers or boron?
Which group?
Well, the other three.
No, I use naphthalene-based plasticizer.
What type of plasticizer?
Naphthalene-based plasticizer.
Okay.
Yeah.
You should ask a lady from MC. They collaboration with Waters successfully applied as plasticizer for their geopolymers. And they're looking for also.
Okay. Thank you.
So, Georgia?
Yeah, I've been using different polymer-based
Thank you.
plasticizer. Newer polyacrylic acid. Never tried boron so far.
Okay. Thank you.
Rob?
So instead of using plasticizer, we selected a material that has already the good viscosity. There are so many different materials available. So first we want to use the best of the material. If we want to enhance it, we use the smallest amount of plasticizer. Why? Because the more plasticizer you add, it disturbs the chemistry. So if you have already a very good raw material, or you have selected someone else, a material that is good for your application, good for your specs, and so on. In fact, I'm thinking about some fly ashes. Some of them are very fluid. So you don't need to add any.
Completely agree. Cool. Next question. Another one. Right?
Maybe I misunderstood it, but I have a question regarding the way you call or what you call indirect or indirect printing.
Yes.
Between you and
Well,
you.
yes.
Because what you do is to fulfill a mold, and then you get rid of the mold. But you call indirect printing a different thing,
Yes.
right? Can you explain that difference of of the way you call it?
Well, for me, indirect printing is you have the mold and you throw something in it. This is indirect.
That's an inverse replica.
Yeah,
Right.
whereas for
Yeah,
Zola,
I
it is regular printing with a different material.
So I would call, I think there are kind of technology and like negative replica or indirect replica of a 3D printed part. Indirect printing, like by the American Standard Association, is the printing on a powder bed or on a slurry in a way that you're not printing your part, but you're just setting your part with something which can be either a binder or a laser. That's like official term for indirect printing. But yeah, I think that could be indirect, like negative replica or all the 3D printed parts still.
In other words, we use 3D printing and a fast prototyping for making a complex shape. This fast prototyping for complex shape mold instead of using silicone, because anyway you have to make the positive, the mold is the negative, and we have already everything in one process.
So what they do, it would be for you direct printing, because they make the mixture before they pump it into a terminated shape. Right?
Yes. Okay. Here.
It works. So first of all, thank you very much for this very interesting presentation. I'm impressed, not only because some of our products have been used, but very, very interesting, and that shows to us all, and I think it's the 6th time I attend to the geopolymer camp, and it shows that there is now really development. Joseph, I think you agree that there are, this 3D thing is really something inside, and I'm really impressed. I have one question to the EPISCOR project concerning crack formation and shrinkage. I mean, if you print these huge elements, which is at the end one piece with several meters, a lot of volume, how's the crack formation and shrinkage in this case? Because I suppose you have a lot of tension usually inside the part, the piece, concerning the drying and the reaction.
In reality, the most difficult thing to do this kind of recipe for me was to adapt Russian sand that are not selected are this. This is Russian sand, no choice. You can use this bulk of sand, but you can choice, you can sieve, you have to adapt the rest of recipe to this raw materials. And I do this work. I did this work in January with 50 degrees outside, and so it's not easy to think. But probably I'm lucky. I was lucky. I obtained a balance between sand. That is one type of sand. So is completely closed. The curve is naturally closed because it started from 0 to up to 125 millimeters. So all curves is quite stable and permit that with the percent that I found right ratio between the binder, liquid, and aggregate. Not an easy work because I have to find in one day, one shot, and so I'm very proud to have to this product. And I think in laboratory shrinkage is not so high to create cracks, visible crack. Maybe I haven't microscopes or electronic microscope to make research in this way, but that this is what I'm arrived until now. It all is improving.
So even today, after some months, how old is the building or the pieces that you've done? How many months or
4 months?
4 months. So even today, and if you have a look on the durability, you can have no deformation or crack formation, because you know all in the construction industry usually.
You can see this
yeah.
is from
this is a piece, but if you
from
have a
the
look
21 of January.
Okay.
So air conditioned and not stored with cure, not in heat condition. So only room temperature.
So even the big piece you have made with the
yeah.
Okay. Okay. Thank you.
So next.
Just I'm going to a comment because you are so precise on the term that you're using. He said that fly ash is harmful with more fluid. That's not correct. Okay, in the rheology term, fly ash is not harmful with anything. It's because of the spherical shape. Be careful when you're using these terms for people who are working with rheology studies and so on. And also the lady and the Italian lady. Other guys actually they use the right term, which is a thixotropic fluid, but they don't use it. If you're going to please, because it brings a kind of confusion when framing the article from a person who doesn't have any idea about 3D printing, but I know about the rheology. So I need to figure out what type of rheology is it. But if you say thixotropic, easily I can figure it out. So it's better to be more precise with respect to the term that you're using. I think it was perfect. To be honest, you did a great job.
Okay.
Thanks.
I have one comment. They want thixotropy, he wants fluidity. And in fact, it's the same. So both are injecting. Thixotropy in the pump and fluidity outside. And you achieve thixotropy by different ways. So we got a thixotropic system, which we don't need it since we don't have mechanical pumps, so we do it by hand. So we had to have super high fluidity. So everything is open. We depend on the equipment, and we depend on a lot of things. And the results will be what you have to do. Okay? Yeah?
Yes, I just want to have a question. First, thank you very much for your presentation. It's very interesting. I have a question about have you studied the possibility to combine geopolymer with steel fiber in order to make steel fiber reinforced geopolymer for application in civil engineering structures?
No, we don't. I'm not. I thought about fibers, natural fibers, only basalt, not steel, because I think about the insulation of the house. Steel is a conductive, so cold can penetrate more easier from the bottom of the walls, and I prefer basalt that is a thermal inductance about 0.03, so is the minimum you can put inside, and could be work not good as a metal, of course, but enough. This is my idea. Probably it's possible to change.
Yeah. No corrosion.
I don't understand this type of question. Why? Then when you are applying your grout, you have the grout and you have chalk fibers coming. So the inclusion of chalk fibers, any kind, within the system is not a problem. The equipment, it is already done, not for the printer. So how do I add my fibers? It is chalk fibers, or is it ropes, or it is rebars and so forth? For me, this is not a problem. It is just a matter of the equipment.
That's because when we add fiber, it can cause some problem concerning viscosity. And
Okay.
yes, and that's why we need to add plasticizers, things like that.
Other question? Yes?
I have a question about standardization. Somebody in the Russian group mentioned a process of standardization of geopolymer for building in Russia. So my question is, for you, how far you are on this process of standardization? And for anybody else, are you aware, maybe also you, Professor Davidovich, are you aware of any other standardization in any country of the world to include geopolymers for building industry?
Yes, sorry, but this is for tomorrow morning.
I'm not there.
I will discuss it privately.
I can answer about the standardization. We are now, let's say, in the beginning of preparing the text of the standard, but it is already approved by the government that this standard will be. It is only the question of time, and the financing has also been approved for the standard. So the work has begun. But it takes...
The main obstacle is to overcome cement producers and those who are not familiar with geopolymers. That's why we have to rely on our previous history and make a standard not for geopolymers, but alkali content materials with alkali, both alkali activated, because the people in the panel who will sign the approval for the standard, they're familiar with alkali activation materials, but they don't know what is geopolymers. We don't know this. So we have to make a general standard for all applications, like it has in Ukraine. They have a national standards for alkali activated materials, and you can make construction buildings with geopolymers as well.
Okay, next question.
I have a quick question for Ralph. Ralph, how did you test for tensile strength, and did you use a standard method?
We used Brazilian method. Okay? Want you to know. That is split strength.
Yeah.
Yeah.
Okay, thank you.
This one. Next.
So about the third presentation, can you evaluate the different costs between the actual technology for producing technique ceramic and your technique?
Regarding this, it costs 80 cents to manufacture the plastic mold and 20 cents of material. I don't talk about the workforce and the time spent on this. And it's not comparable because the way to manufacture a ceramic with very high temperature requires a very different process.
Okay, fine. So, he's not aware of the geopolymer technology. Ceramic has to be fired at 1200 or 1400, depending on what you are asking for, before you get the strength, where there is at 60, 80 degrees C. And then where the ceramic, it can be probed to up to 1200 and so on. Or not, or use at 200. Or if you ceramic, even use that tin at room temperature, like your dishes, or like your freeze, like everything, has to be fired. Otherwise, it has no resistance. We don't need to fire. I like the difference. And because it is done at low temperature, we master the shrinkage. So we have exactly the dimension. We master the thermal shock. You know what we have inside. These are totally different products. And the high-tech ceramic now, good, is to go through the geopolymer because it is easier to manufacture and then goes up to high temperature to produce a super high resistant ceramic. This is the revolution.
Yes.
Next. Okay, time for coffee.
And this is the original with the correct center. This is in the center of the color from the iron rich and very not dry. So we have a little problem to calculate the right amount. In laboratory is one way yes, we use only the center.
You know how is it? Are you how is it?
Yes. We have both.
So I know how much raw material,
because she asked for this solution for me, and it was not enough.
Because I have a card, so this is what my this is from today's from yesterday. I no one mentioned of this this fact because all the yes. So I'm happy that now I'm working
because I want to sell my printer to some company. Thank you. So I'll email you. So because also I am working for a company. So their main target is to make smart structures. During printing, I can integrate sensors that will detect the temperature outside, and using that sensor, your doors will be automatically open close. for smart structures, because Singapore, you know, it's a very small country, so everything need to be stacked up.
Yeah.
So they want smart structures, more greener, more sustainable.